Hello, good morning, guys. Am I audible? Am I audible? Okay. Okay. So in the last lecture, we have started the chapter that is memory management, and we have seen some of the basic concept that is required for this chapter. Okay. So we have seen the concept regarding uh, address binding, that is compile time, load time, and execution time, as well as also we have seen what is the logical address space, physical address space, and logical address and physical address. Okay. So logical address, the address from the virtual memory or logical memory, or we can say it is from the backing store. Whereas the physical address, the address from the physical memory, that is nothing but your RAM. Okay, and physical address space, it is a set of physical address, nothing but set of your addresses of RAM. Logical address space, set of logical address, nothing but the address from virtual memory. Okay, also I've seen the concept of swapping, in which the process can be swap in as well as swap out as per our requirement. Okay, the process that is taking from backing store into the main memory process called as the swapping, swap in, whereas the process shifting from main memory into the backing store is called as the swap out. Okay, so when we require this swap in and swap out, that we will see after in this chapter. Okay, so now the next bit is the regarding the memory allocation. Okay, how to allocate memory for the execution of the processes. Okay, so the memory that is available, definitely the memory is referring the main memory. So this main memory that is available, that is allocated either in the contiguous manner or non-contiguous manner. So first we will see the contiguous model. So in the contiguous memory allocation, memory is divided into the two partition. One partition is for the operating system and second partition is for the user program area. Okay, definitely when we are allocating memory, that memory should be allocated in the contiguous manner in continuous memory allocation. Okay, in the continuous memory allocation, we are allocating memory in contiguous manner. We have the full memory of RAM. ओके, आपल्याकडे रॅमची फुल मेमरी अवेलेबल आहे आणि ज्यावेळेस आपण मेमरी अलोकेट करतोय त्यावेळेस आपण ती कंटिन्युअस मॅनर मध्ये अलोकेट करतोय. सो डेफिनेटली वेन वी आर अलोकेटिंग मेमरी, when we start the process or when we start the PC, then the operating system, it is loaded from your hard disk into the main memory. Okay, and from that point the memory allocation start. Okay, रॅमचं allocation कधी स्टार्ट होतं, ज्यावेळेस आपली बुटिंग प्रोसेस स्टार्ट होते. बुटिंग प्रोसेस नथिंग बट युअर लोडिंग ऑफ युअर OS into the from hard disk into the RAM. Okay, so from that point the allocation, continuous allocation of the memory is started. Okay, so operating system, you can load into the low memory as well as into the high memory. Okay, low memory, that is the memory resides in the lower part of the RAM, or the higher memory memory resides at the higher area of the RAM. Okay, higher area and lower area means, lower area means it will start from 0 to afterwards. Okay, lower area means start from 0. Higher area from end, that is from higher area. So you can store the operating system one of the part either into the low part or into the high part. Definitely it should be in the contiguous manner. It should be in a contiguous manner. So operating system, it can be loaded into the lower memory or into the higher memory. But since the is interrupt vector is reside in the lower part, or it can indicate to the lower memory, so it's better to locate operating system into the lower memory. Okay, so because of this constraint or because of this situation, it is always choosing that OS should be reside into the low memory. Okay, because of this interrupt vector. So when the memory allocation start, the first part is the allocation of memory to the operating system. So first that allocation done, and after that, now that first part is the OS, and the remaining part is reserved for the user program. Okay, whatever the process that you want to execute, you can execute this process from this user program area. So in the continuous memory allocation, the memory we have divided into the two part. First part where the operating system loaded, and second part where it is not loaded, or where the free memory area is, or where the we can call the area is the user program area is present. Okay, so user process which then held in a higher memory. Okay, if you are loading operating system into the lower memory part, then the user process can held in the higher memory. Now, before starting this, we need to understand how to protect this memory, or how to protect this contiguous memory from any other external user. Okay, memory मध्ये जर आपल्याला एखादी प्रोसेसला किंवा डेटाला जर सिक्युअर करायचं असेल, तर डेफिनेटली वी नीड टू protect the access to that particular area. So for that purpose, we are using two register. One is the relocation register, and second is the limit register. Okay, whenever the system want to access any part of area, then it require relocation register value as well as limit register value. So relocation register contain the value of smallest physical address, or we can say it contains the value of physical address, whereas the limit register contains the range of logical address, or we can say length of the logical address. Okay, so each logical address, it must be less than the limit register. Okay, I think we have discussed this part in the last lecture also, that is the relocation register and the limit register. So with the help of this relocation register and limit register, the CPU can access memory. Okay, CPU can access the memory. So first, whenever the logical address that comes to the CPU, then it will first check whether this address is less than the limit register. If it is less, then it will transfer, then the controller will transfer, and it will add this address with the relocation register, and then afterwards it will get the physical address. Okay, so how this address transfer performed, that will see in detail. But the memory protection that is required for this allocation, or the memory protection that is required to access the process or any code and data, that protection is provided by using the relocation register and limit register. Okay, now the allocation, it can be a contiguous or it can be a partition. Okay, so in the contiguous allocation, we have seen in the last lecture that the memory in the single partition, the memory is divided into a single partition. Memory, it is divided into single partition, and only one process we can load into the memory area. Okay, if you compare with this one, so OS taking one part. Okay, now neglect that part. Okay, now don't consider that part. The part that is available is only the user program area. Okay, जे काय प्रोसेस तुम्हाला एक्झिक्यूट करायचे ते सगळे तुम्हाला युजर प्रोग्राम एरियामध्येच एक्झिक्यूट करायचे. आणि सिंगल पार्टिशन मध्ये काय होतं की जेवढी ही मेमरी आहे सिंगल प्रोग्राम एरियाची, तेवढी सगळी मेमरी हा एकच ब्लॉक, एकच होल म्हणून कन्सिडर केलं जातं. आणि ज्यावेळेस तुम्हाला एखादी प्रोसेस एक्झिक्यूट करायची असेल, टोटल एरियाचा process, that only single process will be loaded into this full memory. That process will take the full control of this memory. Okay, so this part is allocated, this whole area is allocated to only one process in single partition. So in single partition, and when that process is complete its execution and terminate, then only the second process will enter into system, and in that case also only one process will take the control of this full area. So in the single partition, only one process can be executed at a time. Okay, only one process can execute at a time. So that was not the sufficient way. So that's why the scheme of the multiple partition allocation comes into the picture. So in the multiple partition allocation, memory is divided into the number of block or number of hole. Okay, so hole is nothing but it is the block of available memory, and this uh, holes, it may be a various size, and these are scattered throughout the memory. Okay, so generally your memory, full memory is divided into the holes, and these holes, it can be a variable size or it can be a fixed size. Okay, so we are considering in this example, we are considering that the holes are of the various size, and all these various size holes are scattered throughout the memory. म्हणजे नथिंग बट काय होतं की रॅमची जेवढी काही मेमरी आहे ओएस ची मेमरी सोडून, ओके, रॅम तुमची डिवाइड होताना, रॅमची मेमरी डिवाइड होताना आपण ओएस ला काही पार्ट देतोय आणि बाकीचा पार्ट आहे तो एक्झिक्युशन साठी ठेवतो. तो आता ओएस चा पार्ट तुम्ही कन्सिडर करूच नका, OS part consider करूच नका. Consider that remaining part which is available for the execution. So that remaining part is divided into the multiple partition or multiple hole, and that holes, it may be a various size. That holes may be a various size. Holes same size चे पण असतात, but that scheme is different. आपण जी scheme discuss करतोय, that scheme is the multiple partition with the various size. So the holes we are considering at this example is, at this scheme is, the holes are of the various size, and these all holes are scattered throughout the memory. So when the process arrives, it is allocated contiguous memory from a hole large enough to accommodate it. So when a process arrives, then first it will check that whether the hole is available for that size or not. Okay, first the scanning will perform, and in that scanning it will check that whether the hole which is required for the process, it is available or not. Okay, definitely by the size, that size the hole available आहे की नाही, that is first it will check, and if it's available, then it will allocate it to that process. So operating system, it maintains information about allocated partition and free partition. Okay, now consider this example. Suppose, okay, consider here the first picture. The memory is divided, and one portion it is allocated to the OS, that is representing here, and remaining portion that is available for the processes. Now suppose the processes that is occupied memory is process 5, process 8, and process 2. Okay, that means your memory is divided into the three parts. Memory, it is divided into the three parts, and first part is allocated for the process 5. In the second part, process 8 is allocated, and in the third part, process 2 is allocated. So at this stage, process is the memory is divided into the three parts, and each part contains one process. Now suppose that process 8 has completed its task. Process 8 has completed its task. So definitely it will terminate and it will deallocated from the memory. So when it is deallocated, then that portion of memory become free, so other process can allocate memory from this area. So suppose process 9 come and it require, and it is then this process 9 will get the memory from that portion. And suppose the process 9 is not required that much memory which is free at this moment, then it will take only some part of that available free portion and it get occupied. So the remaining portion is still free for the allocation. Okay, this portion is still free for the next allocation. So suppose next the process 10 comes and it is searching for the free block, then that process can be allocated into the free portion of the memory. So in this diagram you can see the process 10, it is allocated, and uh, the remaining portion that is indicated here, still some portion is remaining, then in that case that portion is uh, available for the next processes. So like that, the memory is allocated in this manner. Okay, so for the different process, the memory can be allocated in this manner. Okay, now take the real-time example. Okay, now take suppose there are 5 processes which is indicating in the job queue. Okay, definitely the information of this process it is maintained in the table. So the table, that is the job queue table, it is present over here. So in this table, it contains the information of process name, then memory that is required for the process, and the time that is required for the execution of the process. Now suppose at the initial stage we have the RAM, that is allocated memory from the RAM is 0 to 400K to the OS, and from the 400K to the 2560K, the memory is available for the different processes. Okay, 0 to 400 that is allocated to the operating system, and the rest part of the memory, okay, that is remaining part is 2160K. It is available for the execution of different processes. Okay, so when operating system start to allocate the memory to the processes, then it will first check the first process, that is P1. P1 it requires memory 600K, so it will select the process P1 and allocate the process from 400K to the 1000K. Okay, the memory that is available from 401K to the 1000K. So it will allocate this process P1 to the free memory. And afterwards, it will go to the second process P2. It will take the process P2 with the size 1000K, and it starts its allocation from 1000K up to the 2000K. Similarly, it will check for P3, which requires 300K. It will check how much memory is available, still memory is available, that is 560K. So it satisfies the request of 300K. So it will allocate process P3. Now, how much memory is remaining? Remaining memory is 2560 minus 2300, that is 260. Available memory is now 260K, 260 kilobytes. Then in that case, it will check how much memory is required for P4, which is 700K. So this request cannot be satisfied since the available memory is only 260K. Okay, available memory is 260K, required is 700. So it will keep P4 on a waiting state. It will keep P4 as well as P5, because P5 also requires 500K. So it will keep the P4 and P5 in a waiting state, and it will start execution of all these three processes. So after 5 seconds, okay, since the execution time requirement for this P1, P2, P3 is 10, 5, and 20 seconds. So after 5 seconds, P2 will finish its execution. P2, it will finish its execution and it can remove from the memory. It can remove from the memory. So after removing this P2, this block that is from 1000K to 2000K, it may available for the further process. Now this block of memory is free. So this free block, it can be allocated from the other processes. So operating system, it will remove this P2 and it will check whether this P4 and P5 request can be satisfied or not. So first we'll check for the P4 where 700K is required and available is 1000. So it will allocate P4 in this area, in this free area. So the P4, it will get allocated from 1000K to 1700K. But for P5, it required 500K and available memory is 300K here and 260K here. If you combine this, then definitely the total memory that is available is 560K, which is satisfying the request of P5, that is 500K. But since the contiguous memory is required in contiguous memory allocation, okay, where we are studying the scheme of contiguous memory allocation. So in the contiguous memory allocation, for any process, the contiguous memory is required. Okay, contiguous memory allocation मध्ये तुम्हाला प्रोसेस साठी contiguous memories पूर्ण पाहिजे. Splitting memory is not acceptable. तुम्हाला complete memory, contiguous memory available पाहिजे. So ह्या केस मध्ये memory 560K ची available आहे पण दोन पार्ट मध्ये आहे. It is not in a contiguous manner. So that's why the operating system cannot allocate this P5 into the memory. Understood? Okay, so why it is not, it cannot allocate? Because available memory is not in a contiguous manner. It is in non-contiguous manner. So that's why this P5, it cannot be allocated in the memory. So when the execution of, okay, now P4 get allocated, P4 require 8. So in the memory, P1, P3 and P4 is there. So definitely P1 will finish its execution earlier before the P3 as well as P4. So when the P1 complete its execution, then it will remove from the memory and the size of the P1 is 600K. Size of the P1, which is the 600K, is now available for other processes. Okay, now this much memory, this block is available for the allocation of other processes. So OS again will check what the size of the block that is available. It is 600K. Then it will check what is the size required for the P5 is 500K. So it is satisfying this request. So it will allocate P5 from 400K. For the 400 to 900, P5 get allocated. P5 get allocated. So in this manner, the multiple partition allocation scheme work. Okay, in this manner, the multiple partition allocation scheme work. What happened here? At the initial level, all the memory is available. Full memory is available. Afterwards, the memory, it is get divided as per the size of the processes. जसे जसे प्रोसेस सिस्टम मध्ये एंटर होत गेले तसे तसे त्याचे साईज, त्याचे होल्स, त्याचे ब्लॉक पडत गेले आणि त्यानंतरची रिक्वायरमेंट ही as per that block it is going to allocate it. Okay, so this is the working of multiple partition allocation, and definitely this is the dynamic allocation because this partition is doing dynamically as per the process arrived. The allocation is performed according to the size. Okay, so this is the dynamic storage allocation. So now what is the problem? Okay, definitely there are some problem in the dynamic storage allocation. So first is, what is the dynamic storage allocation problem? The first problem is how to satisfy a request of size n from a list of free holes. Okay, how to satisfy a request of any size of memory or size of n from a list of free hole. Okay, so suppose you have the number of free holes, and suppose any request of the process comes, then the question is which hole should be allocated to the processes, on which basis the hole should be allocated. So for this purpose, there are three strategies. Okay, for this allocation purpose, there are three strategies: first fit, best fit, and worst fit strategy. Okay, to the allocate this block, for the allocation of this block, we have three strategies. First is the first fit strategy, best fit strategy, and worst fit strategy. So in the first fit strategy, we are allocating a first hole that is big enough. We are allocating first hole that is big enough. That means suppose the process P1 arrived required the 100K, and suppose OS starts to scan the whole memory for the 100K block. ओके, एखादी प्रोसेस समजा एखाद्या प्रोसेसची रिक्वेस्ट आली आणि त्या प्रोसेसला 100K ची मेमरी पाहिजे, तर त्या केसमध्ये ओएस काय सर्च करेल की रॅम मध्ये 100K चा ब्लॉक किंवा नियर अबाउट 100K चा ब्लॉक अवेलेबल आहे का नाही. ओके, डेफिनेटली तुमच्या रॅम मध्ये 100K चे किंवा त्यापेक्षा मोठ्या साईजचे किंवा लाईन साईजचे सगळेच ब्लॉक अवेलेबल आहेत. 100K चे पण आहेत, 100K चे जास्त पण आहेत आणि त्याच्या कम्पॅरिझन आहेत. देन इट विल फर्स्ट चेक. डेफिनेटली रिक्वेस्ट सॅटिस्फाय करायची असेल तर तुम्हाला 100K किंवा त्यापेक्षा जास्त साईजची पाहिजे. मग त्या केसमध्ये आपल्याकडे तीन स्ट्रॅटेजी आहेत: फर्स्ट फिट, बेस्ट फिट आणि वर्स्ट फिट. फर्स्ट फिट मध्ये काय होतं, रिक्वेस्ट आली, इट विल फर्स्ट चेक. मग सपोज पहिला ब्लॉक तुमचा 50K चा असेल, रिक्वायर्ड साईज किती आहे 100K, तर 50K ला सॅटिस्फाय होते का, नाही होत. त्यावेळेस तो 50K ला स्किप करेल. इट विल सर्च द सेकंड ब्लॉक. सपोज सेकंड ब्लॉक असेल तुमचा 109K चा, 109K चा. देन दिस ब्लॉक कॅन सॅटिस्फाय द रिक्वेस्ट. This block can satisfy the request. It will allocate that block. Definitely size त्याची 9K ना जास्त आहे. Then also it will allocate it. That is the first fit. सुरुवातीला जो बेस्ट फिट त्याला सापडेल, सुरुवातीला जो फिट असलेला ब्लॉक असेल ज्यामध्ये ती प्रोसेस रिसाइड होऊ शकेल, असा ब्लॉक अलोकेट करणे. दॅट इज द फर्स्ट फिट. सो इन दिस केस, ओके, फर्स्ट फिट मध्ये तुम्ही पूर्ण मेमरी स्कॅन करत नाही. ओके, तुम्ही पूर्ण मेमरी स्कॅन करत नाही. तुम्ही फक्त काय करता, मेमरी तिथपर्यंत सर्च करता जोपर्यंत तुम्हाला फर्स्ट ब्लॉक असा सापडत नाही जो की त्या प्रोसेसची रिक्वेस्ट सॅटिस्फाय करू शकते. ओके, फॉर एक्झाम्पल सपोज 109च्या ऐवजी सपोज तुम्हाला 500K चा ब्लॉक असता, तरी पण तुम्ही तो 500K चा ब्लॉक अलोकेट केला असता. वाय? बिकॉज इट इज द फर्स्ट फिट. पहिल्यांदा तो ब्लॉक सापडला आपल्याला. म्हणजे पहिला जो कोणताही ब्लॉक असू द्या, जो त्याची रिक्वेस्ट सॅटिस्फाय करेल, दॅट ब्लॉक विल गेट अलोकेटेड. दॅट इज द फर्स्ट फिट. बेस्ट फिट. In the best fit, it will check the fittest block which satisfy the memory exactly or near very close to that. Means for example, suppose 100K ची रिक्वेस्ट असेल, प्रोसेसची रिक्वेस्ट 100K ची असेल, मग त्या केसमध्ये OS काय करेल, पूर्ण मेमरी स्कॅन करेल, पूर्ण मेमरी स्कॅन करेल आणि चेक करेल की 100K चाच ब्लॉक अवेलेबल आहे का नाही. मग सपोज मेमरीमध्ये 101, 105, 110 असे ब्लॉक अवेलेबल असतील, तर त्या केसमध्ये सगळ्यात बेस्ट कोणता आहे, 101. 101. Why? Because instead of 105 or 110, as compared to 105 and 100K, it is fittest for that process. So that's why it is get allocated. So that kind of strategy is called as the based fit. Allocate the smallest hole that is big enough to hold that process. So in this case, we are searching the entire list. Okay, entire list. The process has the list of free blocks. So this whole list it have to search unless the order by size. Okay, so this type of strategy, it is a slow, but it allocate a small fragment to the process. So your wastage of memory is not in this case as compared to first fit. फर्स्ट फिट मध्ये पहिला ब्लॉक जर 110 चा असेल आणि बेस फिट मध्ये जर तुम्हाला 101 चा मिळाला, तर त्या केसमध्ये 9K ची मेमरी तुम्ही सेव्ह करताय. सो दॅट्स वाय द बेस्ट फिट इट इज अ it has the advantage in with respect to the memory. Okay, you can say you can save the memory in base fit strategy if you compare it to the first fit. And third is the worst fit. So in the worst fit, again you have to scan whole list or whole memory, and but you have to find the largest hole. You have to find the largest hole. So for this purpose also you need to search entire list. ओके, ह्या केसमध्ये आपल्याला एंटायर लिस्ट सर्च करायला लागेल, पण एंटायर लिस्ट सर्च केल्यानंतर आपण काय सर्च करतोय, त्याचा लार्जेस्ट होल, आणि ते लार्जेस्ट होल आपण अलोकेट करतोय. That is called as the worst fit. So in the first fit and base fit, this is the better than worst fit in terms of speed and storage utilization. First fit and base fit, these are the pretty much better than storage utilization as well as regarding the speed. But thing is that for the first fit and worst fit, you need to scan whole memory, whereas in the first fit you may not scan the whole memory. If you get the whole block of if you get the big enough hole first, then you can stop the searching at that point. So in this case, it may possible that you require the full you need to scan the whole memory also. Okay, ज्या केस मध्ये समजा तुमच्याकडं ब्लॉकच जर एनफ नसेल, तर त्या केसमध्ये तुम्हाला पूर्ण लिस्ट सर्च करायला लागेल डेफिनेटली, किंवा ब्लॉक जर लास्टला असेल तर त्या केसमध्ये तुम्हाला पूर्ण लिस्ट सर्च करायला लागेल. पण शक्यतो फर्स्ट फिट मध्ये पूर्ण मेमरी सर्च करायला लागत नाही. जर पहिल्यांदा ब्लॉक सापडला, you can stop your search at that point only. But in the base fit and worst fit, you need to compulsory search entire list or entire memory. So clear this first fit, base fit and worst fit. Is it clear to all? Okay, so now we can go to the fragmentation. What fragmentation? Okay, so fragmentation it is of two types. One is fragmentation and second is the external fragmentation. So in the internal fragmentation, the allocated memory, it may be a slightly larger than the requested memory, and this size it differs is memory internal to the partition but not being used. Okay, that means the process or the allocated memory, it is diagram you can see. Suppose the two process P7 and P45 are. Now suppose P7 requested for the for the block, and suppose the block that is available okay, so P7 and P43, these two blocks are present in the memory, and rest memory that is available. Suppose the available memory size, it is the 18,462 bytes. Sorry, the available memory is the 18,464 bytes, and suppose the request come for 18,462 bytes. So the block which is large only by 2 bytes. Okay, block it is big only by 2 bytes. So if such scenario is there, then in that case the whole block that is allocated to that processes. ओके, तो सगळा ब्लॉक त्या प्रोसेसला दिला जातो. ह्या केसमध्ये प्रोसेसची रिक्वायरमेंट आहे 8,462 ची, पण त्याला अलोकेट किती केलाय 18,464. ह्या केसमध्ये 2 bytes are extra allocated. Definitely these 2 bytes are not used by that particular process, but it is get allocated to that process. So definitely this is the wastage. This is the wastage of the memory. These 2 bytes memory is not used by process also. So this type of fragmentation is called as the internal fragmentation. त्या प्रोसेसच्या आतमध्येच मेमरी आहे जी की तुमची वेस्ट जाते. That is the internal fragmentation, and this type of fragmentation occur when memory is allocated in fixed size pieces. ज्यावेळेस तुमची मेमरी फिक्स साइज पीस फिक्स memory allocation असेल, when the memory allocation is fixed, then in that case the internal fragmentation is occur frequently. The second type is the external fragmentation. So in the external fragmentation, the total memory space is exists to satisfy requests, but it is not a contiguous manner. ओके, प्रिव्हियस मध्ये पण केस आपण बघितली होती, आता ह्या केस मध्ये पण तेच आहे की जेवढे काही प्रोसेसची रिक्वेस्ट आहे, प्रोसेसला जेवढी काही मेमरी लागणार आहे, ती मेमरी ऍक्च्युली टोटल मेमरी अवेलेबल आहे, तेवढी टोटल मेमरी अवेलेबल आहे, बट दॅट मेमरी इज नॉट इन अ कंटिजियस मॅनर. That memory is not in a contiguous manner. So same example here. Here you can see that 900K to 1000K, 100K block it is available. From 1700 to 2000, again that 300K block is available. As well from 2300K to 250 or 2560K, that 260K block is also available. So total 660K memory is available, and the process requesting size is only of 500K, but still that memory you can't allocate because memory is not available in a continuous manner. So when such case is there, then that type of fragmentation is called as the external fragmentation. This fragmentation is the external fragmentation. So in the external fragmentation, the total memory space, it is satisfy the request, but since it is not a continuous manner, that memory is cannot be used, and that memory is, we can consider it as the wastage of a memory. It is not the total wastage, but since it cannot be used, in that case it is just wastage type. So that's why when such scenarios happen, then we can say that the external fragmentation is occur. So in both cases, in the external as well as in the internal fragmentation. So especially the external fragmentation, the total memory is available, but still you cannot execute the processes. So Definitely, you need to solve the problem of this external fragmentation so that the better utilization memory you can done, as well as the time required for the execution of the process, it can also be reduced. So one solution to reduce external fragmentation is the compaction. One solution to reduce this external fragmentation is compaction. So what is compaction? So compaction means shuffle the memory contents to place all free memory together in one large block. What we are doing compaction? In the compaction, we are shuffling the memory content. We are shuffling the memory content to place all free memory together. Okay, so in this case, if you consider this scenario, since the 900K to 1000K, this memory is free. So shuffle P4 from 1000K to the 900K. What we are doing here? We are shuffling P4 from 1000K to the 900K. So what happened in this case? Since the memory is shifting or it is shuffling, so P4 it is now occupying memory from 900K to the 1600K. 900K to the 1600K. So the next block, that is the P3. Now shuffle that P3 from 2000K to the 1600K. P4 कुठं संपलं होतं 1600K ला. म्हणजे त्यानंतर डायरेक्ट P3 स्टार्ट करा, P3 तिथून अलोकेट करायला स्टार्ट करा आणि त्याची मेमरी कुठपर्यंत अवेलेबल आहे तुम्हाला 900K. So after 900K, so all your free memory is now available in a contiguous manner from 1900K to 2560K. So this is called compaction. तर कॉम्पॅक्शन मध्ये आपण काय करतोय की जेवढी काही मेमरी आपल्याला लागणार आहे ती सगळी मेमरी आपण एका साईडला शफल करतोय आणि जे काही तुम्हाला फ्री मेमरी अवेलेबल आहे ती तुमची दुसऱ्या एंडला असेल. सो दॅट मेमरी इज युअर कंटिन्युअस मेमरी. सो यू कॅन अलोकेट दॅट कंटिन्युअस मेमरी to the other process for execution. Okay, getting so compaction, it is possible only if relocation is dynamic. If the relocation is static, that means if the relocation is done at load time or compile time, in that case the compaction is not possible. Compaction, it is possible only if relocation is dynamic. If we are doing the relocation dynamically, then only compaction is possible. If relocation is static, you cannot perform this compaction. Can you tell me the reason? Can you tell me the reason why it is not possible? Why compaction is not possible if relocation is static? Are you listening me? कमी फक्त एकदा मी एकटाच बडबड करतोय आपलं तुमचं फक्त चालू आहे बाकीचं काही काम. Are you listening properly? Are you getting all the things that I am teaching? सगळ्यांचं लक्ष आहे ना का आपलं फक्त मी बडबडत चाललोय? Anybody has the answer? Why compaction is not possible if relocation is static? What is meant by static relocation? That is the first question. Then only you can kind of understand why it is not possible. If you don't know the static relocation and dynamic relocation, then It is not possible to answer this question. That is why compaction is not possible for the static relocation. What is happening in static relocation? Static, yeah, static relocation. So in the static relocation, your addresses are fixed. In the static relocation, in which the relocation is done at load time or compile time, the physical addresses are fixed. For example, suppose if you consider that this relocation is static, then in that case, for the P5 or for the P4, 1000K, if this is the address provided at load time or compile time, then this address is fixed. You cannot allocate P4 other than 1000K. This address is fixed. So if the address is fixed, then you need to execute from that address only. जर P4 चा ऍड्रेस स्टॅटिक असेल तर त्या केसमध्ये तुम्हाला P4 ला 1000K पासूनच लोड करावं लागेल, कारण त्याचे सगळे ऍड्रेसेस फिक्स आहेत. सगळे ऍड्रेसेस फिक्स आहेत. So that's why this relocation, it is not possible if the if compaction is not possible if relocation is static. But if the relocation is dynamic, that means address is not provided at load time or compile time. If the address is provided at execution time, then it means you can change the addresses at any point. So that's why if you need to do compaction, you can change the address of P4 from 1000K to the 900K. Okay, dynamic location मध्ये you can change the address. You can change the address. So that's why it is possible. If you can change the address, then only you can shift the process from 1000K to the 900K. So that's why the compaction, it is possible if relocation is dynamic. Okay, so you can see this example. So of a system, it contains the process P1, P2 residing at 300 and 500. The block of 400K, it is free. Then again from 1000K to 1200K, P3 is allocated. Then 300K, it is free. And again from 1500K to 1900K, P4 is allocated. And after that, the whole of 200K, it is free. So in that case, the total free memory, it is 900K. 400 plus 300 plus 200. Total 900K is available. So after the compaction, this 900K, it will be present at the one end, and the allocated memory, it is present at the other end. Okay, are you getting? Okay, now go to the next concept, that is the paging. Okay, so continuous allocation, that part is finished. Now we are shifting to the paging. So in the paging, we are dividing physical memory into fixed size block, which is called as the frame. And we can divide the logical memory into block of the same size, which is called as the pages. Okay, so what is the frame and what is the page? Don't get confused. In frame means we are dividing the physical memory. Now physical memory is nothing but your RAM, memory from your main memory. So the main memory, it is divided into the fixed size of block. Main memory, it is divided into the fixed size of block, and this block called as the frame. And the logical memory, nothing but your virtual memory or memory from the backing store. That memory is divided into the same size of block, and this block is called as the pages. So always remember, the pages means memory. Pages are block from virtual memory or logical memory, and frame, it is the block from physical memory or main memory. Okay, so frame, block from main memory, pages, block from logical memory. Generally, this size of the block, it is in the power of 2. The size of the block, it is in the power of 2. So that means the size, it may be a 2 byte, 2:1, 2:2, that is 4. So size, it may be a 4 bytes, 2:4, 2:3, 8. The size may be a 8 or 16 or 32 and so on. So generally, the size is between 500 bytes to the 8192 bytes. Generally, the size is between 512 bytes to the 8192 bytes. So that is nothing but your 2:9, that is 512. And what is this 28192? Is it 2:14? Yeah, it may be. Okay, so generally the size is in this range. Okay, and it is always in the power of 2. So in the paging, we keep track of all free frames, and to run a program of size n pages, we need to find a n free frame and load the program into that frame. Okay, first what we need to do, when we place the process into the virtual memory, then this process is divided into the pages. ज्यावेळेस आपण कोणताही प्रोग्राम, कोणतीही प्रोसेस ज्यावेळेस तुम्ही व्हर्च्युअल मेमरीमध्ये प्लेस करता, बॅकिंग स्टोअरला प्लेस करता, then this virtual memory is divided into the pages. So automatically the process or the program that is you are loading into the backing store, that process is divided into the pages. And definitely the size of the page is equal to the size of the frame. So whenever any page is transferred from backing store to the main memory, then in that case, since the size of the frame and page are same, you can easily transfer the page. Okay, पेज ची आणि फ्रेम ची साईज दोन्हीची पण सेम असते, त्यामुळे एक पेज आपण डायरेक्टली फ्रेम मध्ये ट्रान्सफर करू शकतो. So for that purpose only the size is keeping free. Now also you need to track all the free frame. Definitely the whole physical memory is divided into the frame, and some of the frame are get allocated and some of the free. Then in that case, OS needs to keep track of all these free allocated or sorry, all this free frame as well as all allocated frame दोन्हीचा ट्रॅक त्याला ठेवावा लागतो. So whenever you need to run a program of size n pages, first you need to find that n free frame and then only you can load the program. Okay. ज्यावेळेस तुम्हाला एखादी प्रोसेस एक्झिक्यूट करायची असेल तर डेफिनेटली सिन्स दिस प्रोसेस इज डिवायडेड इंटू द पेजेस, सपोज एखादी प्रोसेस असेल ती प्रोसेस डिवाइड झाली 10 पेजेस मध्ये, मग 10 पेजेस मध्ये पूर्ण प्रोसेस असेल तर त्या केसमध्ये यू नीड 10 फ्रेम्स फॉर द एक्झिक्युशन. यू नीड 10 फ्रेम फॉर द एक्झिक्युशन. ओके, सध्याला आपण कन्सिडर करतोय की पूर्ण प्रोसेस ऍट अ टाइम आपण लोड करतोय. सो दॅट्स वाय वी आर अज्युमिंग दॅट ऑल पेजेस आर लोडेड. All pages are loaded. So in that case, you need to find that much amount of frame in which the process is divided into the pages. If the 10 pages are there, you require 10 frames. If 20 pages are there for a process, then you need 20 frames. Okay, so n free frame required for the n size pages. So this is the logical view of paging. But general paging is why required, because in the continuous manner you have seen that if memory is available continuous, then only you can load the pages. If continuous memory is available, then only you can load the pages. मग त्या केससाठी तुम्ही काय कॉम्पॅक्शन यूज केलं, कॉम्पॅक्शन करून एका ठिकाणी आपण कंप्लीट मेमरी अलोकेट करू शकतो. मग त्याचा एक दुसरा वे काय आहे, दुसरा वे आहे की जिथे जिथे मेमरी अवेलेबल असेल तिथे तिथे आपण प्रोसेस लोड करू शकतो. दॅट इज द सेकंड ऑप्शन अँड दॅट इज वी आर स्टडिंग. दॅट मीन्स वी रिक्वायर नॉन कंटिन्युअस अलोकेशन. वी आर टॉकिंग अबाउट द नॉन कंटिन्युअस अलोकेशन, अँड फॉर दॅट नॉन कंटिन्युअस अलोकेशन वी हॅव द स्कीम ऑफ paging. So in the paging, the allocation is the non-contiguous. Paging doesn't require contiguous allocation of memory. Whenever the free frame is available, you can load the page at that frame. Only need is that you need to keep the track. You need to keep the track. You can consider here. You can look at the diagram. Look at the diagram. Suppose in the logical memory, the page 0, page 1, page 2, and page 3. In the 4 pages, your process is divided. In the 4 pages, your process is divided completely. So for these 4 pages, you required 4 frame. Requirement is that you required 4 frame. Definitely this 4 frame, it may be contiguous or it may be a non-contiguous, doesn't matter. So in this example you have seen that this these pages are allocated in non-contiguous manner, in which the frame number 1 contains page 0. Your page 0 is get allocated in frame 1. Similarly, in the frame 3, page 2 is get allocated, and frame 4, page 1 is get allocated, and frame 7, page 3 is getting allocated. So that means you can store the page at any number of frame. कोणतेही पेज कुठल्याही फ्रेम मध्ये अलोकेट करू शकतो. Only thing is that you need to keep track of that. Thing is that you need to keep track of that, and we are keeping that track by using the page table. We are using page table to keep the track of allocation of the pages in the frame. So here the page table is there. So in the page table 2 entries are there. One entry is for the page number, and second entry is for the frame number. Okay, so you can see in the page table 0, which indicates the page 0, and that page 0 is stored at the first page, stored at the frame 1. So you, from there, by looking, so OS is, it search the page table. Okay, OS always access the page table to access the page from the main memory. So to actually first will OS visit to the page table, it will see where the page 0 is reside. It get the address of one frame, so it will go to the frame 1 for page 0. Similarly, page 1 is stored as the frame 4. So at the frame 4, your page 1 is present. So that track is keep in the page table. Similarly, for page 2, frame 3 need to access. Where is the pair 3? Yes, here is the frame 3 in which page 2 is stored. And similarly, page 3, it is present at the frame 7. So frame 7 where the page 3 is present. So this reference, okay, this mapping between the page and frame, it is done at page table. And remember, each process has page table in memory that maps page number to physical addresses. For every process, there is a page table. Okay, this is the question for your MCQ. So remember that for every process, there is a one page table. Definitely, there is a page table for every process where the mapping between page number and physical addresses is present. And one more thing, remember, the page table is present in RAM only, in your main memory only. That is also question for the uh, MCQ or any competitive exam. Okay, remember, page table always reside in the main memory. Okay, so page table in which the mapping between page number and physical address is present. Okay, so is there any problem till now? Any confusion? Have you understood all things? Okay, then draw this diagram, page table. Take 5 minutes, draw the diagram. Then we'll go for the paging addressing. Take your time. Okay, finish. Okay, so paging addresses, we'll take this in our afternoon session. Okay, I'll stop here. I'll continue from paging addresses in afternoon session. Okay, attendance for division A, roll number 1,
Present.
2,
Present, sir.
3,
Present, sir.
4,
Present, sir.
5,
Present, sir.
6,
Present.
7,
Present, sir.
8,